Hey everybody, I just want to talk to you for a moment about using and connecting representations. The assignment we did, everybody did a really nice job talking about the different representations students might use when solving the tasks that you posed, but there was a little bit of a misunderstanding about what it means to connect representations. So that's what I want to talk to you about real quickly. So just as an example, I'm going to use this task that's here. I just did a quick Google search and found a task that was at least a level 3 to 4. And this is a systems of equations task. So this is a task that a teacher uses at the beginning of her systems unit, where she actually has a box and she calls it a mystery box, and this clue is on the top and there's stuff inside the box. In this case, inside the box are tickets. So she says this box contains 22 tickets. Some are adult and some are child tickets. Adult tickets are worth $5 each. The children's ticket is worth $3 each. If the total value of the tickets is $74, how many of each are there? And they are to think about, see if they can come up with a solution for this, and then open the box and see if they're right. So clearly just kind of a traditional systems of equation task. However, because it's stripped of any directions of which way to go, that raises the level of it because you could use any strategy. So thinking about that, I brainstormed what strategies might students use. And I've got 5 of them here. The first is setting up actually setting up equations and solving it using different algorithms. I used substitution here. A student might have also used elimination, or there's lots of options. I just chose one just to say if one representation might be using an equation and using sort of an algorithm to solve it. The second representation here is a student using a table. It's a pretty detailed table on this one. Here we've got the number of adult tickets in the first column, the number of children's tickets in the second column, and the amount of money that would be in the box with that combination, and actually showing how it was figured out. So for the first row, one adult ticket times $5 plus 21 children's tickets times $3, because it's $3 each, would be $68. And this student would probably maybe didn't recognize it right away and went, oh wait, 74 is what I was looking for, there's my answer. Student 3 jumped and used a graph, but again, like student number 1, we see a setting up of the equations, but instead of solving it algorithmically using substitution, graphed it and see the intersection there. Didn't write a sentence that we can see here, but let's assume written somewhere is there are 4 adult tickets, 18 children tickets. Student 4 also used a graph. This time, notice the equations are set up slightly differently, and the solution down here is at the point 18.4. However, let's assume this person also wrote down there are 18 children's tickets and 4 adult tickets. And student 5 used a table as well. There's just less information in this table. We see the combinations of X being adult tickets, we assume. Y, maybe we assume those are children's tickets. Looking at the combinations and the totals on the far left. Or far right. So these are different strategies, but when we're talking about representations, we're talking about what is actually recorded on the paper. So the representations here, number 1 is an equation or a set of equations. Number 2 and number 5 are tables, and number 3 and number 4 are graphs. So those are different types of representations. Now, if we're wanting to see connections among them, that's where we start looking for not just the connections in the strategies that are similar, but what do they actually have in common? So for example, we know in the original problem it says that there are 22 tickets. How is that represented in each one of these? So on the first one, it's represented right here, and I talk about how they did that. In the second one, it's represented here, but it's also represented right here. Our third, again, same thing here, as well as 22 tickets total. And in this case, we can't see it. The 22 tickets comes from the summing of these 2 columns together. So every one of these pairs adds up to 22. So that's where we see the 22 there. And I'm sorry about the sound. I'm actually in the car right now. My husband just stepped out and closed the door. And down here, on number 5, 22 is again the sum of each of these columns. So when we talk about connections, we're looking at where is 22 represented in each one of these. So in other words, where is the total number of tickets represented in each one of these representations? That's the connection there. If we talk about every ticket is worth $5. How is that in each one of these representations? That's a connection that can be made amongst them. Number one, we see that right here, $5 times the number of adult tickets. Does that show up in person number two, student number two's representation? That multiplying by $5 is all the way down in this column. Okay, where does that show up in number 3 and number 4? And this one's kind of interesting. So we can see the 5 right here, and we see the 5 right here. How does that show up in this graph? You have to think about that a little bit. So when we talk about making connections among the representations, that means when you see some key feature of the representation. So for example, we have this down here in representation 5, this equals 74. Where does that show up in each of the others? So that's what we talk about, what we mean when we are saying we are looking for connections amongst these. Another example, if you look at 2 and 5, we see this whole row of numbers here that is the same. Why are they the same? Well, we just have more information up here in number 2 because we can see where they're coming from. So that's another connection that can be made. So I hope that helps clarify a little bit. If you have questions, please let me know. If you would like to do some revisions on your tasks, you're more than welcome to do so. Just let me know when they've been uploaded, and I'm happy to take a look and get some information back to you. Do remember that, as we read in our book, the reason we do this is so we can help students see what make sense of each other's representations, make sense of each other's strategies, make sense of the task and the way it's represented mathematically. It's not for no reason. It's how we're learning to make sense of each other's reasoning. And in your EdTPA, when it comes to your instruction, you will have to call out where you've used different strategies and how you've made, or different representations and how you've made connections amongst them. That will be in task 2. So it's really important that you get some practice doing this. Thanks. Hi, I'm back. I thought of one more really important representation in here that I didn't point out the first time, or connection that I really hope you can see, and that is right here. If we take a look at that equation there, that system of equations, where is that in this table? That's a conversation I definitely want students to be having, because both are very good strategies. Number 2 is not nearly as efficient. It would take a while depending on the situation, but they represent the same thing. And you'll notice right here, these two adding up to 22 all the time, all the way down, is your A plus C equals 22. And then right here is your A times 5 plus C times 3 is equal to 74, as we're building that up to this place where it actually works. So we have that same structure all the way down. This right here representing your A and this representing your C, and that's a connection amongst these two very different looking representations that you would hope your students would be able to talk about, and eventually take that over to the graph as well. So that's it.